Let's talk about the quantum numbers, which are the numbers assigned to every electron and that tell us about the position of electron outside the nucleus completely. There are four types of quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Principal quantum number tells us about the shells. It was firstly used by Schrödinger. It is represented by n. In the Bohr's atomic model, the concept of shell was given that outside the nucleus there are certain energy levels. In these energy levels, the electrons revolve. So these energy levels or shells defined as 2D spatial areas outside the nucleus. Later on, it was found that the structure of atom is three-dimensional. So principal quantum numbers tell us about the shells outside the nucleus in three-dimensional axis. There are certain shells K, L, M, and N. The shell closest to the nucleus is K, which has a value of principal quantum number 1. For L, the value of N is 2, for M, it is 3, and for N, it is 4. The principal quantum numbers values range from 1 to infinity. They can never be 0. So the electron revolving in K shell will have a number 1 in its electronic configuration. Same is the case for L, M, and N. The number of electrons in a shell or orbit can be found out by using 2n square formula. The principal quantum number for K shell is 1. Multiplying 2 with 1 gives us the answer 2. And we know that the K shell can accommodate 2 electrons. Same is the case with L shell, but now you have to replace principal quantum number with 2. And it gives the answer of 8, that the L shell can accommodate 8 electrons. For M orbit, the number of electrons that can be filled out are 18. The second quantum number is azimuthal quantum number that tells us about the orbitals S, P, D, and F. S stands for sharp, P stands for principal, D stands for diffused, and F stands for fundamental. The azimuthal quantum number is represented by L. The azimuthal quantum number value for S shell is 0, for P it is 1, for D it is 2, and for F it is 3. How many electrons S, P, D, and F can accommodate? You can find out their values by using formula 2 into 2L plus 1. Just put the value of azimuthal quantum number L and you will find out the number of electrons that S, P, D, and F orbitals can accommodate. By putting the value 0, you find out that S orbital can accommodate 2 electrons. By putting L with 1, you find out that P orbital can accommodate 6 electrons. By replacing L with 2, the number of electrons D can accommodate can be found out, which are 10 in number. The F orbital can accommodate 14 number of electrons. One of the defects of Bohr's atomic model was that when a spectrometer of high resolving power is used, the spectral lines split up into several very fine lines. This type of splitting is known as the fine structure in spectrum, which says that only principal quantum number is not enough to tell the position of electron outside the nucleus. This problem was resolved by presenting the azimuthal quantum numbers. The second defect in the Bohr's atomic model was that when the spectral lines are exposed to external electric or magnetic field, they split up into the several fine lines. This effect was known as Zeeman and Stark effect. The splitting of spectral lines by applying external magnetic field is known as the Zeeman effect, which says that there are other quantum numbers that must be needed to locate the electron outside the nucleus. So the magnetic quantum number was presented. It is represented by M. It is also known as the orientation quantum number. Magnetic quantum numbers tell us about the position of electron in three-dimensional axis. Either it is along x-axis or y-axis or z-axis. Due to the probability of finding the electron in three-dimensional axis, the orbitals are degenerate. The magnetic quantum number also tells us about the degeneracy of orbitals. Degeneracy is the presence of multiple orbitals of same energy within one orbital. For s orbital, the azimuthal quantum number is 0 and magnetic quantum number is also 0. The magnetic quantum numbers start from 0, plus minus 1, plus minus 2, plus minus 3, and so on. For s orbital, the L value is 0 and M value is also 0. This magnetic quantum number value 0 tells us that the orbital is non-degenerate. And this is how we found out that s orbital has probability of finding the electron equal in x, y, and z direction. And it is non-degenerate. In the case of p orbital, the azimuthal quantum number is 1 and magnetic quantum number is 0 plus minus 1, which is showing that p orbital has three space orientation: 0, plus 1, and minus 1. As p orbital can split up into three equivalent energy orbitals, it has threefold degeneracy. This degeneracy is represented by px, py, and pz. These three orbitals on removal of external magnetic field appear as single p orbital. But when the magnetic field is applied, the p orbital splits up into three different orbitals which are differently placed in space but have the same energy. As p orbitals split up into three orbitals, it is known as threefold degenerate. In the case of d orbital, the azimuthal quantum number value is 2 and magnetic quantum number value is 0 plus minus 1 plus minus 2, which is showing that d orbital can have the 5 spatial orientation and it is 5-fold degenerate. It is represented by dx square minus y square, dz square, dxy, dyz, and dzx. For f orbital, the azimuthal quantum number is 3 and magnetic quantum number is 0 plus minus 1 plus minus 2 plus minus 3. 1, 2, 3, 4, 5, 6, 7, showing that f orbital is 7-fold degenerate. This is how magnetic quantum numbers tell us about the degeneracy of orbitals and the special orientation of electrons outside the nucleus. The fourth quantum number is spin quantum number that tells about the spin of electron. Either it is clockwise or anti-clockwise. It is represented by S, and for clockwise spin, it has a value of plus 1 by 2. For anti-clockwise rotation, it has a value of minus 1 by 2. As you know that an orbital can hold two electrons. So one of the electron has clockwise rotation and the other has anti-clockwise rotation. It was found out by Goldsmith and Uhlenbach in 1925. They found out that an electron while moving in an orbital around the nucleus also rotates about its axis, and due to its rotation there is a magnetic moment as electrons are the charged bodies, so they rotate and generate the magnetic field, and due to this magnetic field there is a magnetic moment. The direction of this magnetic moment tells us about the spin of the electron. If the direction of magnetic field is downward, the spin is anti-clockwise. If the direction is upward, it is clockwise rotation. Now let's discuss the shapes of orbitals. As you know that s orbital is non-degenerate, the probability of finding electron in s orbital is same all around. So it is spherical in shape. However, if it is present in the K shell, its size is smallest. 1 is showing the principal quantum number and S is showing the orbital. So 1s is the s orbital located in K shell or first shell. Its size is smallest. S orbital located in second shell has a greater size than 1s, and so on. So while moving away from the nucleus, the size of s orbital goes on increasing and it is spherical in shape. The probability of finding the electron in s orbital is same all around. While p orbital has threefold degeneracy. The special orientation for electron in p can be along px, py, and pz, along x, y, and z axis. The shapes of p orbitals are dumbbell. It was found out by magnetic quantum number or orientation quantum number that the d orbital has 5-fold degeneracy by dxy, dyz, and dzx. These orbitals have their lobes between the axes. The remaining two orbitals have their lobes along the axis, which are dx square minus y square and dz square. The dz square has only two lobes. The shapes of f orbital are quite complicated. This was all about the quantum numbers, their types, their outcomes, and the shapes of orbitals. Like, share, and subscribe to my YouTube channel, and thanks for watching.